Greetings. So we are finally working on some accumulation in our calculus class. And this is the practice free response question for our upcoming test. So I'm going to read through it and then we will attack each of the three parts on separate slides. There's a leak in a water tank where water is draining out of a small hole. As time passes, the hole gets bigger. The function w prime of t equals 1/2 t models the rate at which water escapes through the hole in gallons per hour. So time is measured in hours, and then the amount of water is measured in gallons. At time t equals 0, there are 17 gallons of water in the tank. In other words, w of 0 equals 17. And then we have these three questions that we have to address. So letter A, how much water drained out during the first 3 hours of the leak? Letter B, we're asked to create an accumulation function, w of t, that computes the amount of water in the tank at time t. And then for letter C, what is the domain of this function? And we're referring to w of t there. Okay, so I'm going to address these three. It's not going to take that long. This is a relatively straightforward accumulation problem, but I'll walk you through each piece of the process, and hopefully this will help you have a better understanding of how to attack these problems. Here we go. So in problem A, or in part A of this problem, we are asked to find out how much water leaks out in the first 3 hours. Okay, so since this is the rate at which the water is leaving the tank, to find out how much water leaks over the course of the first 3 hours, we simply set up a definite integral which will add up the change and ultimately give us our total over the 3 hours. So something like this, I'm going to say, excuse me, we'll call it gallons. So we'll call it G. G is going to equal, man, I'm having trouble with this thing today. G is going to equal the sum of the area under the curve here from 0 to 3. So we simply integrate from 0 to 3. That's the first 3 hours of w prime of t, which is 1/2. My computer keeps giving me the business. 1/2 t dt. And I'm simply going to use the fundamental theorem part 1 to compute this total. So the antiderivative of 1/2 t is t squared over 4, right? It's 1/2 times t squared over 2, which is t squared over 4. And we're going to evaluate that over 0,3. So what I'll do is, I'll put the 3 in, and that will be 9 over 4. So I'm going to have 9 over 4 minus 0 over 4, which is 9/4 or 2.25 gallons. So even though I'm going to write it as a fraction there, when we answer this question, we want to use common sense language, and it's asking how much water, so I'm going to say 2.25 gallons. And that is the answer to part A. Let's see if I can highlight this thing a little bit. Oh yeah, look at that. I'm going to highlight it in yellow there. Okay, so to just add up the amount of change, you integrate over the interval. And that's what we did. It's kind of like doing area, right? We're doing time multiplied by gallons per time, hours multiplied by gallons per hours, and then we end up with gallons. We're just doing the area under the curve. Okay, let's go ahead and take a look at letter C here and see how that goes. Okay, moving on to letter B, I should say, not letter C. Oh, that picture looks really blurry to me. We'll see how it comes across on the video. You can always rotate back to the original slide or just look at your paper because it's the same problem. We're asked to create an accumulation function, w of t, that computes the amount of water at time t. Okay, so here's how this models. We're going to make w of t, and I'm going to put t in red just so you can see what's going on here. remember, we make an accumulation function. Our format is f of x equals f of a plus the definite integral from a to x of f prime of t dt. That's our format. Okay. Essentially what I'm going to do is replace the f's with w's, and my a is going to be 0. My a is going to be 0 because that's my initial condition right here. We need this. My a is 0 and my w of a is 17 here, so we can get this thing set up. And then there's one little subtle trick here that we have to be careful of. So my water in the tank, W of t, the water at time t, is going to be the 17 gallons. Now remember, this rate is the rate at which the water is leaving the tank. So that's actually a negative rate. So when I integrate this, I'm going to subtract instead of add because I'm losing water. And my limits of integration are going to go from 0, which is my initial time, up to this time t, which is the value that we're inputting into the function. Now, let's just double check our format here. When we have f of x, we had the letter x here, and then the rate function we wrote with a different variable. We need to keep an eye on that and do the same thing here. Since I'm using t to represent my independent variable here, when I write down this rate function, I'm going to actually have to change letters. So I'm going to put 1/2 x dx. That's a subtle but important distinction. The variable that you're using for your input, the one that's in your limits of integration, this t here, the red one, it can't match the variable that's in your function here. It's not going to match the x and the dx. So just be careful with that. This, however, is that accumulation function that they asked us to create in letter B. We made a function that calculates the amount of water in the tank at time t. The water starts at 17, and then we're subtracting the amount of water that we accumulate over the course of time. For example, for W of 3, we do 17 minus 2.25, which is something like 14.75, right? We would subtract off the water that left. Okay, so that's my accumulation function. Don't do anything crazy. We're just building the function for part B. We weren't even asked to use it for anything. Okay, now let's talk about letter C on the last slide, and then we'll be wrapping this video up. Okay, so we're moving on to letter C, which asks us what the domain of this new function that we made is, right? We want to know the domain of this thing. And I just rewrote the function here so you can see it. So let's talk about this. This function computes the amount of water in the tank at a certain time. I think you'll agree that the physical limitations of this problem dictate that as soon as the water's empty, this function's useless, right? As soon as we've emptied out 17 gallons, there's no more water in the tank, and the function needs to be 0 the rest of the time, right? So that we have to limit the domain on this thing for it to make sense. And we do that by restricting the time that we're going to put into this function. So I think you'll agree the lowest time we can put in is 0. So for our domain, we're going to have 0 be the bottom boundary. What we're really trying to find is when is the thing empty, because that'll be our upper boundary. Well, to do that, let's just think this through. We just need to know when the amount of water in the tank is 0. So in other words, we need to solve W of t equals 0. So let's do that. Let's just set our function 17 minus the integral from 0 to t of 1/2 x dx equal to 0. We're not going to panic because we know how to evaluate this definite integral. We're going to use that fundamental theorem of calculus that we used in part A, right? We're just going to evaluate this thing. So it's going to be 17 and then minus, it was, what was it, x squared over 4 was our antiderivative, and we'll evaluate that from 0 to t. And then set that equal to 0. So this is going to be 17 minus, and then this will be t squared over 4. minus 0, right? That's how we do that fundamental theorem. So in other words, 17 minus t squared over 4 is going to equal 0. Let me continue that over here. 17 minus t squared over 4 equals 0. With a little bit of algebra, I think you'll agree that we get t squared equals 17 times 4. And 17 times 4 is 68. So t squared equals 68. And so when I take the square root, I get whatever the square root of 68 is. Okay, square root of 68, which is approximately 8.246 hours. Okay, so in terms of my domain is from 0, and I'm just going to put the square root of 68. 0 to the square root of 68. If you don't like that, you can also put 8.246 hours. That's the domain of our function. This function only makes sense when there's water in the tank. And as soon as we empty out 17 gallons, we have to stop using this function. Okay, so that's the gist of this problem. We need to spend more time practicing these, I know, but this is another a round of you getting familiar with how we talk about accumulation, how we create an accumulation function for our function values, and then also I like to think about the domain for functions that we make too, because in applications like this, they only make sense over certain values. Okay, that's it for now. This was a quick and sort of clumsy video, but it'll give you a little insight into this problem, and then I'll talk to you when I see you again. Take care.